Hello, in this video I want to show you a comparison between PID and a fuzzy logic controller for a DC-DC buck converter. But first of all, I want to give you a brief introduction. The proportional, integral, and derivative controller is a linear controller that uses the error between the set point, that is, the desired output value, and the real output of the plant. It is extremely known for its simplicity and is frequently used in the control loops in the process industry. It uses this equation to calculate the control effort that needs to be applied to the plant to get that desired value. This equation can be discretized using a set of approximations and give a function of PID discrete equivalent like this. On the other hand, we have the fuzzy logic controller, an advanced control technique that uses fuzzy logic to include the knowledge of a process into account. It is very useful to control nonlinear plants that often don't have a known reliable model, and also it is possible to include the knowledge of a process operators in the form of linguistic rules that relate fuzzy inputs and outputs of a process. A fuzzy logic controller usually uses the error and the difference of the actual error and from the previous step to generate a control effort using this topology. First of all, the inputs are fuzzified into fuzzy variables, quantified through called membership functions that use a value between 0 and 1 to represent the degree of membership of the inputs to the fuzzy variable. Then they are passed to an inference engine that uses a rule base to calculate the output based on the fuzzy variables get from the actual input. Then the result output is diffusified, combining the output of all the rules that were fired. There are several methods for this, like the centroid, mom, etc. For more information, check out the link in the description. In this example, this is the fuzzy logic model that we use, created in the Fuzzy Logic Designer app. It has two inputs, the error and delta error, and the output is delta UK, that is, the change of the control effort applied in one step. The membership functions that we use are the next one: negative, 0, and positive for each of the inputs and output, and they are related by the rules using this mapping. For example, this rule says if the error is negative, that is, the process output is greater than the set point, and the delta error is negative, that is, the error is decreasing, then delta UK is negative, that is, the control effort must be reduced, analog for the other 8 rules. Next, I want to show you the two controllers applied to control a first order plant with this transfer function. For tuning the PID controller, I use the PID tuning app, and for the fuzzy logic controller, I use the following parameters to normalize the inputs and the output. That means that the variables that get into the fuzzy logic controller are normalized and limited. And these are the results. For both the PID and the FLC, the results are very acceptable. Both outputs get very fast to the set point, but the FLC chose to be faster than the PID for this case. The buck converter is a switch DC-DC stepper-down circuit that uses a DC voltage source, a switch, a diode, a coil, and a capacitor to power a load that can be variable. For this reason, it is important to have a control system to keep the output voltage constant. I get this buck converter Simulink model from the MATLAB example using this command. I left you the link in the description. Next, I want to show you the same two controllers to control the output voltage of the buck converter. The input of the system is the duty cycle of the switch, that is, the portion of a period that the switch is closed given a certain switching frequency, the output of the system is the load voltage. I use these two gains to transform the real process values to percentage. That is, the real duty cycle goes from 0 to 1 and the output voltage goes from 0 to 200. But for the controllers, the inputs and outputs goes from 0 to 100%. The buck converter transfer function is the next one, and it can be used to tune the PID controller easily using the PID tuner app. For the FLC, the only parameter that I tuned was the SDU gain to tune the denormalization of delta UDK, and these are the results. The yellow line is the set point, the blue line is the output with the PID controller, and the orange line is the output of the process with the fuzzy logic controller. Same as the previous example, both controllers achieve an acceptable performance controlling the output voltage of the buck converter. Both get fast to set point with zero error in steady state. The FLC gets faster to the set point, but in general, both controllers make a good work, considering that the PID controller is much simpler. Conclusions. Both the PID and the FLC are valid tools. The advantage of the PID controller is that it is simple and robust, easy to tune and fast to implement, but it is a linear controller, and sometimes it can't control a process for all the working points due to the variable parameters in the process. There are several techniques to solve this problem, for example, gain schedule and stack controllers, etc. The FLC is more complex than the PID controller, but it is a simple way to generate a nonlinear controller due to the tunable membership functions and linguistic rules that can make the controller show different behaviors in different working points and situations. In conclusion, the selection between these two controllers depends on the situation. If the plant has almost static parameters and can be bundled by a first order or a second order model, maybe the best way to go is a PID controller. But if that is not the case, maybe a nonlinear controller like the FLC is a better choice. Thank you for watching this analysis. Goodbye.